This is video number 21 in our series of topics in quantum mechanics from Digital-University. In the previous video, we had derived an expression for the rate of change of the expectation value of a certain quantum mechanical observable. If we have an observable K, this is the formula for finding its expectation value. We have derived that in, I think, video number 19. And then its expectation value quite often is abbreviated like this. And what we found in the last video, video number 20, is that the rate of change of the expectation value of the observable equals this quantity, where inside here we have the commutator of the Hamiltonian of the system with the observable. And that's why we concluded in the last video that the Hamiltonian generates the time evolution of the system. And remember, the Hamiltonian is this. It's like the total energy of the system. The momentum squared divided by 2 times the mass plus u of x. But this is potential, and here we're saying the potential depends only upon x, because right now we're discussing quantum mechanical particles that exist only along on the x-axis. Right now we're just restricting ourselves to one-dimensional cases. So let's see then, let's apply this, not just an observable k, but the position x. Remember that that's the position operator. So what that's going to say then is just d dt of x, its coordinate along the x-axis. So, according to the definition, and looks like we may be left out I over h bar from here. Okay, let's apply the definition then. This would be equal to, not the definition, but what we had derived in the last video. This would be equal to I over h bar. And then we would have the commutator. Now this is p squared over 2m plus u of x. That's what the Hamiltonian is. That's the h, comma, not k, but x. So let's see what this commutator is equal to. So this is equal now to I over h bar, and we're going to have commutator of p squared, that we can leave in there for right now. We have p squared over 2m x plus u of x. So that's the expression right now. So we have two commutators. This commutator and this commutator. Well, this one is 0 because this is just simply u of x times x minus x u of x. So this just gives us 0. So right now then what do we have? Now we'll take this to the outside, and that will equal I over 2m h bar, and then from this commutator This is 0. Now, from this commutator, we're going to have p squared x minus x p squared. Now, this is not 0 because we can never determine position and momentum at the same time, and that will deal with it as we work on down here from the equation. But this is not 0 because we can never precisely determine the position and the momentum at the same time. So that's why this is not 0. Okay, what do we have? This is equal to I over 2m h bar. Now, if this was classical mechanics, of course, that would be 0. But in quantum mechanics, there's always the uncertainty principle, so x and p can never be entirely determined simultaneously. So here we have p x minus x p. And now what I want to do, I think, is that in this expression, let's consider it like this. We have I over 2m h bar. We have p x. And let's do this. Let's try subtracting minus pxp, and we'll add it, so we're not adding anything new. And we have this term, minus x p. So here we added and subtracted a quantity, so no net change. Now, for this part right here, for this part of the expression, here we have ppx minus pxp. What happens if we factor out this p? Then we need a colored pen here. Because now what we have then is px minus xp. So here then what we have is this equals I over 2m h bar, and then from here we have this p factored out, so we have p like this, but then this is just a commutator px. That's what this is, if you've written right here. So that's this part of the expression. Now if we go over here to this side, we have p and p. Now here we have px minus xp. So this right here, that would be the commutator px. So we have plus commutator px, the p on the right side. So we have this expression. And this, let us not forget, is the rate of change of the position. Now, let's go back down here for a moment though. And I think it was in video 18 or 19, I think it was video 18, what we determined is that here what we have with px and px, that commutator is minus I h bar. The commutator px. That's equal to minus I h bar. And that was, I think, in video number 18 that we derived that. So what we have then is this is minus I h bar, and this is minus I h bar. So it's getting awfully messy. Let's make some room. Don't need this bar anymore. What we have is this d dt of the change in position equals, that's I over 2m h bar. I over 2m h bar. And then we have this expression right here. P with that commutator plus commutator again, P. That's our expression so far, and we know that that commutator is minus I h bar. Here and here. So let's see what this leaves us. Here we're saying then that this is equal to I over 2m h bar, and here we have minus 2I h bar times P. Like this. So the 2's cancel. I squared is negative 1 times minus, that's plus. So this is equal to, and the h bars cancel. So this is equal to P over M. Like this. And again, I squared, that's negative 1, times negative 1, that's positive. These h's cancel, 2's cancel, and we end up with positive P divided by M. So what we're saying then is that the rate of change of position, when we applied our formula, equals the momentum divided by the mass. And when you think of this in terms of classical mechanics, that makes sense. This is mass times velocity divided by mass is velocity, so the rate of change of position of a quantum mechanical particle is momentum divided by mass, and that would correspond then to the velocity of the particle. And again, the way that we derived this was going back what we derived in the previous video, stating that the rate of change for the expected value of an observable is this quantity right here, with h is the Hamiltonian, and again that's where the statement derives from, that the Hamiltonian generates the time evolution of the system because you're taking the commutator of the observable with the Hamiltonian. Well, in this case, with position just simply being a coordinate on the x-axis, then we just have x in place of k, and then for h, we just substituted if h is equal to p squared over 2m plus the potential term, u of x. And then we just went ahead, just went through the algebra really, and then finally we get this expression. Okay, that's it for this video. Hope that makes some sense now. In the previous video, when we were just working with any kind of operator to derive this, the equations were difficult, but it was a little bit abstract. So hopefully now, seeing an example of this applied to a specific situation makes sense. And then come back now in the next video, we're going to go through the same process again, only now we're going to consider the rate of change of the momentum operator, or the expected value of the momentum. So come back, join us for that video, and that will wrap up our discussion concerning the time evolution of quantum mechanical operators.